So today we're solving October-November 2021 paper 22. Okay. So here we have question number 1. Hydrogen iodide is a colorless gas at room temperature. Explain why HI has a higher boiling point than HCl and HBr. Now if you guys remember this trend from group 17, right? Even though HCl and HCl is the most polar of the three, whereas HBr is slightly less polar, the bond, and HI is the least polar. But in this case, HI has the greatest number of electrons. So over here, the number of electrons is the main factor. Okay, there's no hydrogen bonding here. It's just van der Waals forces due to permanent dipoles, right? And HI, because it has the greatest number of electrons, it has the greatest boiling point over here. Okay, so for this, we're gonna say HI has the greatest number of electrons, has a greater number of electrons, and therefore it has stronger van der Waals forces. Okay, van der Waals forces between molecules. Okay, now the bar chart shows the boiling points of HCl, HBr, and HI. The boiling point of HF is not shown. Hydrogen bonds can form between HF molecules. Remember, hydrogen bonds form when hydrogen is either directly bonded to an oxygen, like in water, hydrogen is directly bonded to a nitrogen, or hydrogen is directly bonded to fluorine. Okay, that's when you have hydrogen bonding. So what would you expect the boiling point of HF to be? Would it be lower than HCl, or would it be the highest of the four? Over here, you would expect HF to have the highest boiling point of all the four molecules because it has hydrogen bonding. Okay, so this is how you would draw the bar chart. You don't need to know the exact value, but you should know that it will be greater than all the others. Okay, like that. Explain your answer. So what would you explain over here? The reason why is because the hydrogen bonds, right? Hydrogen bonds are stronger than van der Waals forces due to permanent ion induced dipoles. Then van der Waals forces due to permanent and induced dipoles. Next part of the question says the standard enthalpy change of formation, delta HF of HI is positive 26.5 kilojoules per mole. Define the term standard enthalpy change of formation. It is the enthalpy change when 1 mole of a substance is formed from what? In its standard state, is formed from its constituent elements, right? Or from the elements, its constituent elements in their standard states under standard conditions. Okay, in their standard states under standard conditions. All right. HI can be formed by reacting hydrogen gas with iodine. The reaction is reversible and an equilibrium forms quickly at high temperatures. So here we have iodine gas since we have a high temperature. Construct an equation for the equilibrium constant Kp for this reaction to form HI. Now if you guys remember, Kp is simply the partial pressure of the product, right? So in this case we'll have partial pressure of iodine, right? And it'll be squared because the coefficient over here is 2, divided by the partial pressure of the reactant. So we have partial pressure of hydrogen is to the power of 1 and the partial pressure of iodine. The equilibrium partial pressures of the gases at 200 degrees Celsius are as follows. Calculate the Kp for this reaction. So you just plug the values in over here. What you have is Hi is 4800 pascals, so that will be 4800 squared, right? That's in the numerator, divided by hydrogen times iodine, that's 895 times 895. So we have 895 times 895. So what does this value come out to? This will come out to 28.8. Okay. And what are the units of this guy? You have pressure squared in the numerator and pressure squared in the denominator. So does this have any units? There are no units here, right? The units, the numerator and denominator, the units cancel out. Okay. State how the value of Kp would change, if at all, if the reaction were carried out at 100 degrees Celsius rather than 200 degrees Celsius. Now remember, first of all, temperature is the only factor that affects the value of the equilibrium constant. Temperature is the only factor that affects the value of the equilibrium constant. Okay. And they've said that the formation of Hi is plus 26.5. Now over here, obviously, this is not the standard formation of Hi, because this is not under standard conditions, right? They're at a high temperature. But do you think this reaction is endothermic or exothermic? So now again, over here, they've given you the formation of Hi from the elements as positive 26.5. Now this is under standard conditions. Now over here, as I said, you're just assume that the delta H is equal to positive 26.5. So we're assuming it's an endothermic reaction, okay? Again, this is an assumption that we're making because this value is for standard conditions. Over here, we don't have standard conditions, okay? Now, if I have an endothermic reaction, what would happen to the value of the equilibrium constant if I decrease the temperature? A decrease in temperature will favor what direction if I have an endothermic reaction? If I have an endothermic reaction here, right, what we realize is that decreasing the temperature will favor the backward reaction, because the forward endothermic reactions are favored by increases in temperature. So here we would say that Kp would decrease, okay? This is again assuming that the reaction is endothermic, okay? So Kp would decrease because, okay, because the reaction is endothermic. Okay, and the reason why is because the equilibrium would shift to the left. Okay. All right. The next part of the question says, Hi reacts with oxygen to form iodine and water. Construct an equation for the reaction of Hi with oxygen. So here we have Hi reacting with oxygen to form I2 and H2O. And now we have to balance this equation over here. So if we balance this equation, how do we balance this equation? First of all, one thing you should realize over here is that for every iodine, right? Iodine, the oxidation number goes from -1 to 0. And for oxygen, the oxidation number goes from 0 to -2. So then, how many iodine atoms would you need for every oxygen atom? How many iodines would you need for every oxygen atom? Right? You would need 2 iodines for every oxygen atom, because the change in iodine is +1, for oxygen it's -2, right? So you're going to need 2 iodines for every 1 oxygen atom to balance the changes in oxidation numbers. So over here I can say that I have 2 Hi. For every 2 oxygen atoms over here, if I just take O2 as I have 1 molecule of oxygen, right? So for every 1 oxygen atom I have 2 iodines, then for every 2 oxygen atoms I would need 4 iodides. Okay, I would need 4 iodides over here. And then I'd have 2 I2 and I'd have 2 H2O. Explain with reference to oxidation numbers why this reaction is a redox reaction. So over here, what's being oxidized? iodine, right? Iodine is being oxidized from -1 to 0, right? And oxygen is the oxidizing agent, so it is reduced. Okay, it is reduced from 0 to -2. So here iodide ions are the reducing agent, right? Hi is the reducing agent and oxygen is the oxidizing agent. The reducing agent undergoes oxidation, the oxidizing agent undergoes reduction. Hi can also be formed by the reaction of I2 with hydrazine. So here they've given the equation for this reaction. State the change in pressure that would occur. State the change in pressure that would occur when 2 moles of iodine react fully with 1 mole of N2H4 in a sealed container at constant temperature. Explain your answer. So here, would I have an increase in pressure or a decrease in pressure? If I have exact amounts of reactants and they're converted into products, for every 3 moles of gas, on the left-hand side, I would produce 5 moles of gas on the right-hand side. So if I kept a constant volume and I increase the number of moles of gas, what will happen to the pressure? Right? If I increase the number of moles of gas or increase the number of gas molecules, right, the pressure would increase, right? The pressure increases. Okay? Because for every 3 moles of gas, that react, right, 5 moles of gas are produced. So there is an increase in number of moles of gas. There is an increase in the number of gas molecules or increase in number of moles of gas. And over here you should say 5 moles of gas are produced. All right. Moving on. In the laboratory, Hi aqueous can be formed in a 2-step process. Right? Step 1, iodine reacts with phosphorus to form Pi3, and step 2, Pi3 reacts with H2O to form H3PO3 and 3Hi. Okay? This is phosphorus acid or phosphoric 3 acid. Over here, phosphorus has an oxidation number of +3. This phosphoric 5 acid is H3PO4, right? That's the one we're familiar with. Draw a dot and cross diagram of Pi3. So phosphorus over here. Okay, let's take X for phosphorus and dot for iodine. Now phosphorus has 5 outer electrons. Okay, it's in the same group as nitrogen. So it's making 3 single bonds with the iodines, right? It's making 3 single bonds like this. And then phosphorus has 2 additional outer electrons. It has a total of 5. 3 of them are in the bonds, right? And the 4th and 5th one are a lone pair, right? And then iodine also has 7 electrons. So we have to show the remaining electrons of iodine. Okay, like this. And then we have this. Okay, so here's the dot and cross diagram for Pi3. Now you can draw it like this or you can draw it with the circles. They're both acceptable. Okay. Name the type of reaction in step 2. What's the type of reaction in step 2? Now if you guys remember from period 3 theory, when we had chlorides of period 3 and they would react with water, right? They would form acidic solution, especially for the non-metals, right? Except for NaCl and to some extent MgCl2, right? MgCl2 is very slightly acidic. All the other chlorides would form acidic solutions. And we're getting the same thing here with the iodide. So what type of a reaction was this? Does anyone remember? Right? The period 3 chlorides, the non-metal chlorides, when they reacted with water, they would form, or the covalent chlorides, when they reacted with water, they would undergo hydrolysis, right? And because they undergo hydrolysis, because they're covalent bonds, right, they're hydrolyzed, and that results in acidic solutions. Okay, these bonds are hydrolyzed. So this is a hydrolysis reaction. Okay. H3PO3 and Hi aqueous are both strong Bronsted-Lowry acids. Give the meaning of the term strong Bronsted-Lowry acid. So first of all, If we say something is a strong acid, what does that mean? Okay. And if we say something is a Bronsted-Lowry acid, what does that mean? Right? So let's actually first look at Bronsted-Lowry acid. Now, Bronsted-Lowry acids are species that donate a proton, right? These are proton donors. Okay, that's one way of defining an acid. That's the Bronsted-Lowry definition, is that they're proton donors. And strong means that they fully ionize in solution. Okay, so they are proton donors. A strong Bronsted-Lowry acid is a proton donor that fully ionizes or fully dissociates in solution. Give the formula of the conjugate base of H3PO3. Now, the conjugate base of an acid is the species that is produced when the acid loses a proton. So when H3PO3 loses a proton, what does it form? It forms H2PO3 minus and H plus. So what's the conjugate base over here? The conjugate base must be H2PO3. Okay, this is the conjugate base. Remember, for an acid, the conjugate base is the species that forms when that acid loses a proton. So when this acid loses a proton, it forms the conjugate base. And for this conjugate base, the conjugate acid is H3PO3. So when H2PO3 minus gains a proton, it forms H3PO3. So H3PO3 is the conjugate acid of this guy, and H2PO3 minus is the conjugate base of H3PO3. Okay, so here the conjugate base of H3PO3 is H2PO3 minus. All right. HI reacts with propene to form a mixture of 1 iodopropane and 2 iodopropane. Identify which of these is the major product and explain your answer. Now, if you guys remember, if you remember the rule is that the hydrogen atom goes on the carbon that has more hydrogens, and iodine prefers going on the carbon with fewer hydrogens. Okay, but the reason why is because when this undergoes electrophilic addition, right? When this undergoes electrophilic addition, it can form two possible carbocations. We can either form this carbocation, right? The hydrogen atom goes on this carbon, so we form this carbocation, or we can have the hydrogen go on the middle carbon, right? In which case we're going to form the carbocation over here. And the iodine will go on this guy. Now, which of these carbocations is more preferred? We have a secondary carbocation versus a primary carbocation. Remember, in the first step, the hydrogen bonds to one of the carbons. So either this one, right, or this one. And then in the second step, the iodine bonds with the carbocation. Now we know that the secondary carbocation is preferred, right, is more stable due to the electron donating or the positive inductive effect of the alkyl groups. So the major product will be when iodine bonds to the second carbon. Okay, this will be the major product, right? 2 iodopropane. Iodine will bond to the second. So secondary carbocation formation will be preferred. So over here, our major product will be 2 iodopropane. Because it forms via a secondary carbocation intermediate, which is more stable, okay, which is more stable than the primary carbocation intermediate. Okay, and the reason why is it's because of due to the electron donating effect, because it is more stable than the primary carbocation intermediate due to the positive inductive effect, or you can say electron donating effect of the alkyl groups. Okay, is more stable than the primary carbocation intermediate. All right. Complete the diagram to show the mechanism of the reaction between HI and propene that forms the major product identified in G part 1. Include curly arrows, lone pairs of electrons and charges as necessary. So they've already given the partial charges here, right? So in the first step, this is an electrophilic addition reaction. So in the first step, what happens is that the electrons from the pi bond, right? The pi bond breaks and the electrons from the pi bond go to the hydrogen atom, right? And at the same time, you have heterolytic fission or heterolysis of this HI bond over here. So both the electrons in this bond go to the iodine, right? And you end up making the carbocation intermediate. Now remember, the hydrogen will bond to the carbon with more hydrogens since you're going to form the carbocation on the secondary carbon atom, right? So you're going to form this intermediate here. So the hydrogen over here will add on to this guy, and you're going to be left with a positive charge on this carbon, right? You have an H and a CH3. And in the second step, what happens is that the iodide, right, it has that extra pair of electrons, right? And now it will donate that pair to form a dative bond with this secondary carbocation intermediate, and you'll end up making your final product. Okay, so this is your product over here. And just a note, just to clearly show that the carbon atom is bonded to the carbon atom, right, in the CH3 group. So let me just show that a bit more clearly over here. We have over here a CH3 like this, and we have a CH3 like this. Okay. Now, next question. Table 1 gives physical data for some of the period 3 elements. Complete the row in the table labeled bonding present in element. Use C for covalent, I for ionic, and M for metallic as appropriate. Now, if you have elements, what type of bonding cannot be present in the elements? Ionic bonding cannot be present in elements, right? Ionic bonding is between a cation and an anion of two different species. So we can already eliminate ionic, right? Now, they've said that, okay, atomic number 11, that's sodium, that's metallic bonding. What about number 2? What's the bonding here? Number 12, sorry, that's magnesium. Magnesium is metallic, right? What about aluminum? Aluminum is metallic. What about silicon? Silicon is a giant covalent structure, so that's covalent, right? Phosphorus, again, covalent, and sulfur is also covalent, okay? And what's the maximum oxidation number for each of these elements? If you guys remember, the maximum oxidation number is the number of valence electrons. So what's the maximum oxidation number for sodium? +1. The maximum oxidation number for magnesium is +2. Aluminum is +3, +4, +5, and then +6 for sulfur, right? Okay. Explain the difference between the first ionization energies of the elements with atomic numbers 11 and 17. So they're saying, the question is essentially asking, why is the first ionization energy increasing across the period? From the first element in the period to the last element in the period, with the general trend that we see as an increase in ionization energies. Why? The reason why ionization energies are increasing across the period, okay, or between 11 and 17, what's happening over here is that, right, across the period, right, the nuclear charge is increasing. Nuclear charge increases, right? So I'll write that across the period. The nuclear charge increases, whereas the number of shells and therefore shielding remain the same. Now this means that the outer electrons are therefore attracted more strongly to the nucleus, and more energy is needed to remove them. More energy needed to remove them. Explain the difference between the first ionization energies of the elements with atomic numbers 15 and 16. So what we see over here is that from 15 to 16 there's a decrease. So from phosphorus to sulfur there's a decrease. From phosphorus to sulfur there's a decrease. Now if you guys remember, for ionization energies the trend looks like this. For ionization energies the trend looks like this, right? What we have is, we have over here this trend, okay? So if you look at proton number or atomic number, right? You look at proton number or atomic number on the x-axis, right? And you look at ionization energy on the y-axis, the trend looks like this, right? You have a generally increasing trend, but what you see is, you see a decrease from magnesium to aluminum, and you also see a decrease from phosphorus to sulfur. Why is that? Right? From magnesium to aluminum, you go from S2 to S2P1. So there's additional shielding from the inner s orbital electrons, right? Whereas from phosphorus to sulfur, you go from P3 to P4. So you have paired electrons in sulfur, but you don't have paired electrons in phosphorus. So this is because of spin pair repulsion, right? Because you have paired, in phosphorus all the electrons are unpaired, right? Whereas in sulfur what you have is, one of the orbitals has paired electrons. So that means that electron, the paired electron, is easier to remove. So this is actually inconsistent with the trend. From S2 to P1 and from P3 to P4, you see that they don't obey the trend. And over here, from P3 to P4 or from phosphorus to sulfur, is because of this paired electrons. There's additional repulsion between paired electrons in the same orbital, okay? That is known as spin pair repulsion, okay? So what you have over here is, right? What you have over here is that from phosphorus to sulfur, what you have is that one of the p orbitals in the sulfur atom, right? Sulfur atom has paired electrons, right? Making the outer electron easier to remove. Making the outer electron in sulfur easier to remove than phosphorus, right? Due to spin pair repulsion or electron-electron repulsion. You can say spin pair repulsion, or you can say inter-electronic repulsion. Okay. Over here, obviously, it's implied that phosphorus, they're all unpaired. Okay. Complete the row in the table labeled maximum oxidation number. So we've already done that. Explain the variation in the anionic radius for the elements with atomic numbers 14 to 17. So here, if you look at the anionic radius, from silicon to chloride, what you have is, you have Si4 minus, you have P3 minus, you have S2 minus, and you have Cl minus, right? All of these have the same number of electrons, but the radius is decreasing. So why is the radius decreasing? All the anions have the same electronic configuration. So why is the radius decreasing? So again, these are isoelectronic species. They all have 18 electrons, but chlorine has the most number of protons in its nucleus. So it has the greatest nuclear charge. So if they have the same number of electrons, since chlorine has more protons, it's attracting those electrons more strongly. Okay, so therefore, the chloride ion is the smallest of the four. Okay, whereas the silicon one would be the largest because it has the fewest number of protons in the nucleus. So over here, we can say that the anions are isoelectronic, right? Have the same electronic configuration, have the same number of electrons, right? However, in this from atomic numbers 14 to 17, what we see is the number of protons, and therefore the nuclear charge is increasing. right? Hence, the outer electrons are attracted more strongly to the nucleus and held closer to the nucleus. And if they're held closer, obviously the radius is decreasing. All right. Use the axes to sketch a graph that shows the trend in melting points of the elements with atomic numbers 11 to 17. Now, let's start with sodium over here. Now, if you look at magnesium, will it be higher than sodium or will it be lower than sodium? Magnesium has, they both have metallic bonding, but magnesium has 2+ ions, right? It has more electrons in the lattice and it has a greater charge, right? So over here, magnesium will be significantly higher. Remember, group 1 metals have a very low melting point relative to other metals, okay? Aluminum is slightly higher than magnesium. What about silicon? Is it higher or lower than aluminum? Silicon has a very high melting point because it has a giant covalent structure or a macromolecular structure, right? Then you have phosphorus, which is a simple covalent compound, P4. Then sulfur is S8 and Cl is Cl2. So over here, what we see is that phosphorus has a fairly low melting point, okay, because it's a simple covalent compound like this, right? Then sulfur is slightly higher because is higher because it has a greater number of electrons, and then chlorine is the lowest because it has the fewest number of electrons. These are all simple molecules. So this is intermolecular forces or van der Waals forces over here. Okay. So in the first three you have metallic bonding, but sodium is very weak metallic bonding. Silicon has a giant covalent structure, so very high. And then the remaining three, the trend you see is because of intermolecular forces and is determined by number of electrons. Chlorine has the fewest number of electrons, so it has the lowest. Sulfur is actually higher than sodium, yes. But they won't expect you to know that. You should know they're about the same. Okay. Dmitry Mendeleev published the first periodic table in 1869. He used his knowledge of chemical periodicity to propose the properties of gallium, a group 13 element. Table 2 gives some chemical and physical data of elements in group 13. Complete the table by predicting values for the missing data. So can someone predict a value for aluminum ki density based on this trend over here? It would be greater than 2.34 and lesser than 5.91. So roughly in between the two. Roughly in between the two would be something like 4, right? What about the boiling point? You see a decreasing trend in boiling point as you go down, right? You see a decreasing trend in boiling point. You go from 3930 to 2470 to 2400. So over here it would be roughly in between these two. So let's just say over here, right? Let's just say 1800 or 1900. Doesn't matter. They'll accept anything from like 1500 to 2300. Okay. And then cationic radius, you see this increasing trend from 0.02, 0.05, and you have 0.08 and 0.095. So roughly in between these two would be 0.065, let's say. Okay. In nanometers. All right. Indium and aluminum are elements in group 13 of the periodic table. Indium has very similar chemical properties to aluminum. Indium reacts vigorously with hydrochloric acid to form a colorless gas and a salt in solution. Indium oxide is amphoteric, just like aluminum oxide, and gaseous indium bromide has the formula In2Br6, so similar to Al2Cl6. This molecule contains coordinate bonds. Identify the formula of the salt when indium reacts with hydrochloric acid. So with hydrochloric acid, if you guys remember, what does aluminum form? Right? It forms AlCl3. So indium will form, the salt it will form is InCl3. Okay? Construct an equation for the reaction of indium oxide with aqueous NaOH. If you guys remember, aluminum with aqueous NaOH forms this anion, right? This is the anion that aluminum forms with aqueous NaOH. So indium will form a similar salt with aqueous NaOH. It's amphoteric, right? So it will react with aqueous NaOH, and the reaction looks like this. Okay, this is an equation you should remember. What you have is it reacts with NaOH and water. It reacts with NaOH and water. Okay, to form this salt over here. You have Na plus. You have Na plus, and then you have over here instead of Al, you're gonna have INOH4, right? So you have Na plus and INOH4 minus. So this is the salt that you're forming. And the balanced equation over here looks like this, okay? You have 2 moles of this, you have 3 moles of water, and you have 2 moles of the salt. Draw a diagram that clearly shows the type of bond present in iron 2Br6. So what type of a bond do you think they're talking about over here? If you guys remember, when two AlCl3 molecules combine, what type of bonding causes their combination? How do they combine with each other? Right? There's dative covalent bondings, right? The halogen donates a pair of electrons, right, to the group 13 element. In that case, it's aluminum. In this case, it will be indium. So what you'll have is you have InBr3. You'll have 2 InBr3s combined, okay, through dative bonding. So you have InBr over here, right? And what you have is this bromine will form a dative bond with a neighboring ion, right? Or iska jo bromine hoga, it will form a dative bond with this ion over here. Okay, clearly show the lone pair and the arrow from the halogen to the indium. Okay, in this case, the halogen is bromine. So this is how you draw the structure. Okay, you're clearly showing the 2 dative bonds over here. All right, the next question that we have here is question number 3. Compound T is an isomer of C6H12. Name T. Now T over here has a 4 carbon chain, right? And when you number this chain, right, you want to prioritize the alkene. So alkene will be carbon number 2, right? Whether you number it from the left or the right, right? Whether you number it from the left or the right, you'll get the alkene on carbon number 2. So what you have over here is but-2-ene, right? And then you have a methyl group on carbon number 2 and carbon number 3. So then what you have is you have 2,3 dimethyl but-2-ene. Okay. Draw the skeletal formula of a structural isomer of T that shows cis trans or geometrical isomerism. Now we have to draw the skeletal formula of an alkene that has this molecular formula that shows cis trans isomerism. So what we have here is, let's just say that I had something like this, right? Let's just make a straight chain, right? Now obviously the double bond can't be on the ends, because on the ends we'll have a CH2. So we'll have 2 identical groups on the carbon atoms. The double bond can't be on the terminal carbons, right? It has to be on the middle carbons. So one of the possibilities that I have is if I just put a double bond here, right? Then I have a hydrogen and a methyl group, and I have a hydrogen and a propyl group. So this guy will this show cis trans isomerism? It will, right? This carbon is bonded to 2 different things, a hydrogen and a methyl, and this carbon is also bonded to 2 different things, a hydrogen and a propyl group. So let's just draw the skeletal formula for this. We have 1, 2, 3, 4, 5, 6. Make sure you just count to double check. 1, 2, 3, 4, 5, 6, right? And then we have a double bond here. And the way I've drawn this, I've actually shown the trans isomer. For alkenes, this exact same alkene can also be represented as the cis isomer, which will look like this. Okay, this is the cis isomer. 1, 2, 3, 4, 5, 6. So either one, this alkene can be represented as the cis isomer or the trans isomer. This is trans hex-2-ene, okay, and this one is cis hex-2-ene. All right. You don't have to draw both. You can only draw. You just have to draw one structure. Each carbon atom in T forms a sigma bond to at least one other carbon atom, as shown. On the diagram, draw the orbitals that represent the pi bond that is also present in T. So the orbitals that represent the pi bond, we have to basically show the pi bond, right? That's the molecular orbital. So the pi bond is above and below the sigma bond. So you just show it like this. Okay. It's when the p orbitals overlap to form this pi bond. State the hybridization of the two carbon atoms between which the pi bond forms. So what's the hybridization of these two carbon atoms? These are sp2 carbon atoms, right? Each carbon is bonded to 3 different atoms. So therefore, we need 3 hybrid orbitals. It has a total of 3 atoms or lone pairs around it. No lone pairs, and is bonded to 3 atoms. So therefore, sp2 hybridization. Okay. sp3 hybridization is when a carbon is bonded to 4 different things. Okay. That's when you have bond angles of 109.5. In this case, you'll have bond angles of 120 degrees around these carbon atoms. Okay, these 4 carbon atoms, the CH3 ones, these are all sp3 carbons. Okay, they're tetrahedral in shape. This is a trigonal planar shape for this carbon and this carbon. A reaction scheme starting with T is shown. Reaction 2 occurs in the presence of a catalyst. Knowledge of the mechanism for this reaction is not required. Give the reagents and conditions for reaction 1. So if I want to convert an alkene to a diol, right? What type of a reaction is this? When I'm adding 2 OH groups over here. So over here, this is when we form a diol from an alkene, right? You're adding 2 OH groups. So there's an additional oxygen being added. This is weak oxidation of alkenes. And the reagents that we used are cold dilute acidified KMNO4. Okay, you can say KMNO4 or you can say MNO4 minus, right? Cold acidified KMNO4. You can write it down the formula this way, or you can write the name down of the oxidizing agent. So it will be cold dilute acidified potassium manganate 7. Okay. State and explain how 2,4-dinitrophenylhydrazine, that's 2,4-DNPH, can be used to detect the presence of V as a product of reaction 2. So here we want to detect the presence of V, right? So what functional group over here will react with 2,4-DNPH? 2,4-DNPH is a test for aldehydes and ketones. So we can clearly see that there's a carbonyl carbon present here. And what we would observe over here is an orange precipitate. We would observe an orange precipitate with 2,4-DNPH. Okay. So again, 2,4-DNPH can be used to detect the presence of a carbonyl carbon. Okay. Specifically aldehydes or ketones. Okay. And we get an orange precipitate. So over here, we would observe an orange precipitate. Okay. Orange precipitate would be observed. And you have to explain why. And this is because due to the presence of a carbonyl carbon, okay, or a ketone in this case, carbonyl group. In this particular case, it's a ketone that's present. The progress of reaction 2 can be monitored by infrared spectroscopy. The absorption caused by OH bonds is always present because water is used as a solvent. Identify 2 absorptions and the bonds responsible whose appearance will change significantly during this reaction. Okay. Now, what they're saying is, for this particular reaction, right, we're going to use infrared spectroscopy to monitor the progress of this reaction. And we can't look at the OH bonds because the OH bonds will, even though they're present here, even once it's converted to V, they'll still be present because we have water. So we can't use OH to monitor the progress. What other bonds can we use? So first of all, let's see. If you look at U versus V, what bond is present in U that will slowly disappear in the infrared spectrum as V is produced? In U, we have the C single bond O, right? That's present over here. The C single bond O is present over here, right? And if you want to monitor the progress, what bond in V will show up on the infrared spectrum that is not present in U over time? Over time, the CO bond will disappear, the single bond O will disappear. And what will show up over time? The C double bond O will show up over time, right? So we can say is that over time, the peak due to C single bond O will disappear and the peak due to C double bond O will appear, right? So if you were using infrared spectroscopy, right, the two absorptions that we can use and the bonds responsible for those absorptions. So the first absorption that we can see in the reactant but not the product is the C single bond O, right? The C single bond O, right? And this will be in the range. Just quote the range from the data booklet, 1040 to 1300 wave numbers, okay? And the other peak that we can use over here is C double bond O, right? That will appear as the reaction progresses, right? And that peak is the carbonyl carbon, and that's 1670 to 1740 wave numbers. Okay, so we've identified the bonds and the absorptions responsible. Okay, we just have to identify, we don't have to explain it in this case. V is used in a wide range of organic reactions. Some reactions of V are shown. V and W are colorless and soluble in water. State what you would observe in reaction 3. Now when V reacts with alkaline aqueous iodine, we produce W. So what type of a reaction is this? Does anyone remember the name for this reaction? Over here you have a CH3. Over here what you have is you have a methyl ketone group. You have a CH3 C double bond O. Right? You have a methyl carbonyl. So this is an iodoform reaction, right? This is an iodoform reaction. If you guys remember, we rupture this double bond and we end up making a salt of the carboxylic acid. So the CH3 is converted to what you see over here is you also see CHI3, and that is triiodomethane. It's a pale yellow precipitate for the iodoform reaction. So the observation here would be a yellow precipitate, right? This is the iodoform reaction. If you have a CH3CO group, right, and an aldehyde or a ketone, aldehyde mein to sirf ethanol hoga, otherwise it's always a ketone, right? Right, this could be a hydrogen or an R group, right? Or if you have this group present, if you have this group present or you have this group present, CH3CHOH, right? One of these two groups has to be present. Either the CH3C double bond O group is present, this group, or you have the CH3CHOH group present. And that again, the carbon can be bonded to a hydrogen or an R group, right? Do you guys remember this iodoform reaction? Right? Either of these two groups would give you a pale yellow precipitate of CHI3 and the CA because the CH3 breaks off. Okay? So this is the iodoform reaction. All right. Moving on. What do we have here? Reaction 3 is a redox reaction. Identify which of the reactants is reduced in this reaction. So this is a redox reaction. So which reactant is reduced? In other words, which reactant is the oxidizing agent here in reaction 3? So in the iodoform reaction, guys, remember halogens are oxidizing agents, right? So the methyl ketone is being oxidized to a salt of a carboxylic acid. So the methyl ketone is undergoing oxidation, whereas iodine is the oxidizing agent, so it's undergoing reduction, okay? Iodine goes from 0 to -1 here and undergoes reduction, okay? So the reactant reduced in this reaction is iodine. Okay. Construct an equation for reaction 4. Use H in the equation to represent an atom of hydrogen from NaBH4. So reaction 4, guys, is the reduction of ketones to form a secondary alcohol, right? And what you have over here is when a ketone or an aldehyde is being reduced, you can use NaBH4, right? For acids, for carboxylic acids, you have to use lithium aluminum hydride. But for ketones or aldehyde, you can use NaBH4. And what happens is two hydrogens are added, okay, to form C6H14O. So the ketone is being converted into a secondary alcohol. All right. X is a mixture of two optical isomers. Draw the two optical isomers in the boxes provided. So if you look at X over here, what we have is we have a chiral center here. We have a chiral center here, right? And what is that chiral center bonded to, right? It's bonded to 4 different groups, 4 different atoms or groups of atoms. It has CH3 and OH and H, and then it has a CH3 thrice. So let's first figure out the 4 different groups bonded to this guy, right? We have a chiral center that's bonded to CH3 thrice, right? We have a CH3, we have an H, and we have an OH, okay? These are the 4 groups bonded to the chiral center here. Again, we have H, OH, CH3, and then CH3 thrice, okay? And if you look at the mirror image of this guy, the mirror image over here, okay, I'll actually draw the mirror plane as well. Here you have the mirror plane. And the mirror image looks like this, right? Whatever's closer to the mirror on the right over here will appear closer in the mirror on the left. So you have a CH3 here, right? On the further side, you're going to see an H in the front, and on the back you have an OH, right? And then on top you still have the same group. It doesn't matter which group you put where. I usually like to put the most complicated group on top because it makes it easier to draw, okay? And I'll also draw I'll show a star. I'll draw the star also to show the chiral center, okay? Both optical isomers of X can be dehydrated to form a single product Y. Give the reagents and conditions required for reaction 5. So reaction 5 is dehydration of alcohols, right? This is elimination of H2O. So what are the reagents or conditions we can use for this? For dehydration of alcohols, you can either use Al2O3, right, alumina, and heat, or you can use concentrated H2SO4 and heat. Okay, so in this case, let's just say concentrated H2SO4 and heat. Okay, you have to heat it strongly for elimination to occur. Okay, so let's say we're just going to use concentrated H2SO4 and heat. Okay, but you can also use Al2O3. This is heating around 200 degrees Celsius, but you don't have to write the temperature here. Okay. Y can form an addition polymer Z. Draw one repeat unit of Z. All right. So if you look at the structure of Y over here, right? We have the structure of Y. So I'm just gonna make a copy of this guy, right? We have the structure of Y over here, and we have to draw the repeat unit of the polymer that it forms. We have to draw the repeat unit of the polymer that it forms over here. Okay. So how do we do that? Well, first of all, take the 2 carbon atoms on the double bond that will polymerize. So we have these 2 carbon atoms here, right? On the double bond that will polymerize. This carbon atom is bonded to 2 hydrogens. And this carbon atom is bonded to 1 hydrogen, right? And it's bonded to this C with the 3 CH3s. So it's bonded to a CH3 thrice, right? And if this polymerizes over here, what do we end up with? Well, the double bond breaks, the double bond over here breaks, right? Or the pi bond over here breaks rather, and then we form this repeating pattern over here, right? So this is the continuation bonds. We have to show them. So this is the repeat unit that we get. Okay. Remember, along the main chain, you'll have these 2 carbon atoms repeating themselves. So everything else will go in the branches. So whenever you have to draw addition polymers, just take the double bonded carbons and arrange everything on those carbon atoms in the top and the bottom, okay? And then you break the pi bond and you form the continuation bonds on those 2 carbon atoms that initially had the double bond. So this is your repeat unit of the polymer, okay? Reaction 6 does not proceed quickly at room temperature. Suggest why this is the case. So if we look at reaction 6, right, they're saying addition polymerization does not proceed quickly at room temperature. So why is that the case? So over here, the question is saying suggest why this reaction doesn't proceed quickly. Now, in terms of energetics, we know that if a reaction is slow, that reaction must have a high activation energy. Okay, so because this reaction isn't proceeding quickly at room temperature because it has a high activation energy. Okay, it has a high activation energy.